Hello guys, in this video we are going to solve this particular problem, and this is the part 1 in which we will do it in DWSIM, and in the next part we will perform the same calculations in pen and paper. So we will check out that how much difference is between them, but let's just try this particular question in DWSIM. So basically it contains the dehydrogenation of ethane, and we need 60% conversion of ethane and need to find out the volume. Okay, so basically what is going to happen that we need to take any reactor, PFR or CSTR, and determine the volume to produce 300 million pounds of ethylene. Ethylene is this one, okay, C2H4 a year. Okay, 300 million pounds a year, and just all the data is given. We just need to simulate this, and let's find out how much volume would be required. So before just opening DWSIM, I just want to show you that because we need to produce this much ethylene a year, so we need to first calculate our feed, that how much ethane we should put to so that after 60% conversion we get this much amount of ethylene. So what basically it means that the moles that would be reacting would actually produce C2H4, and therefore we need to first find out the moles of C2H4 in a better unit, so we can make this pounds to kilogram and year to second. Let's change that first. So it's 300 million pounds and this is per year. Okay, so let's change to 300 million pounds per year to kilogram per second. We need to do that first. There we have this thing, so in kilogram per second, and next we need to find out the particular moles. Okay, so this is amount of mass per unit year, and we need to find out the moles so that we can get the moles of ethane. So what we can do here is that divide the mass by molar weight. So how much mass? Kilogram per second, so we will get kilomoles. Okay, so it's 4.314 divided by, so the molar mass of ethylene would be 24 plus 4, 28. Okay, so we divide it by 28, and this amount of kilomoles per second that we have. Now to find out the moles of ethane that we would input, what we have, that let's say this is my A. Okay, this is my A product giving B plus C. Okay, so this is my A. So what we can see here is that A naught means initial concentration, into XA, the conversion would be equal to CB. So this is my C2H6 ethane, and this B is my C2H4. Okay, so this is the whole reaction. We have this, we have the conversion, so we can actually get my CA naught. So CA naught is equal to CB divided by XA. Okay, so we need to do this particular thing, therefore we will take so this is A gives B plus C, so therefore we will take the moles that we have. This is kilomoles per second. Okay, kilomoles per second of ethylene, so divided by 0.6 because V6, this is kilomoles per second divided by 0.6, so we get the feed divided by 0.6. So it's 0.2567. this amount of kilomole per second of Ca0 of feed of ethane is required. Now let's move on to my DWSIM. So this amount of calculation you have to do it by yourself, because or you can do is change the feed, but it's a simple calculation, so it won't take you much time. Else you have to just assume a feed and just try it out, but that would be not possible here because it will take a lot of time for you to do that. So let's create a new process simulation. Let's quickly take, okay, so next we need to take ethane. Give me ethane, this one, give me ethylene, okay, this one, and give me hydrogen. Where is it? Yes, this one. So we have these three components, quite simple. I will take my Raoult's law only, ideal one. Okay, C5, we need in Kelvin. Mass flow rate doesn't matter over us, but molar flow rate should be kilomole per second. That's important. It should be in ATM, and rest of the thing we can change if needed. Okay, everything's done, but let's put the feed. Okay, so we have my feed, then we have my reactor. Let's take PFR. Okay, and we have this product, so let's name it feed, let's name it product, and let's name it PFR. Okay, simple. Now feed would be at a temperature of 1150 K, 1150 K, and pressure is 5 atm. Okay, now kilomole per second we calculated it, just copy this part, and it's 0.2568. we need to put it, paste. Okay, so this is my feed. It's simply defined as per the problem. Okay, because it will be operating at isothermally, so my feed is at this pressure and temperature, so I will, in the reactor it will be as it is, just it will convert. Okay, so next thing up is that my feed is, so in the compound amounts, mole fractions, my feed is pure, because it says a feed of pure ethane, so I will take it pure. So ethane is 1, this is 0, this is 0, pure ethane, only ethane. Okay, and accept it. Yeah, so 1150 K, 5 atm. Okay, 5 atm, then do this much molar flow rate, and we are good to go. Next, in the reactor we need to specify this isothermic condition. Let's also define the outlet 1150 and then choose isothermic condition. That doesn't matter, we have isothermic default set. Now we need to take the reaction set, so go to insert or edit and simulation settings. We need to go up here, the reactions, and let me add a new, so say R1, reaction 1, and that's okay. Now also let me add the reaction. Okay, So let's add first a reaction of a kinetic reaction. So you can also try to use a conversion reactor, but here you need to just specify the conversion, and that will be just you will specify the conversion and the volume and see if there is no error, then that particular volume is correct. But a better technique is kinetic, because we have the kinetic data given over here, so this would actually give us more accurate results and more faster results. Okay, so the kinetics is given, we will see that, but just let me write the reaction. So the reaction here is methane giving ethylene, ethane giving ethylene and hydrogen. So let's write ethane dehydrogenation reaction and include all of these. The base component would be ethane, because we have the conversion of ethane that is given to us, and the stoichiometric coefficient -1, 1 and 1. Okay, and it's a first order reaction. Okay, elementary reaction, so that's only given. Even the rate constant is given in second inverse, so it's first order reaction. Reverse order is no, it's just irreversible reaction, so there is no reverse reactions, and it's balanced stoichiometry. Okay, so where did it go? So instead of fugacities, we should take molar concentrations as the main unit, and temperature is okay with us. So direct order, we need this pre-exponential factor of RNAs and the activation energy over here. So we have that, but we will see that in a while. Just that the unit amounts, so it's kilomole per meter cube, then it should be kilomole per meter cube second. Okay, that's okay. So we need to specify A and E. For that, we see here that we have the K value for this temperature is given and activation energy is given. So we need to first find out the pre-exponential factor using this thing. What we have here is 0.072 second if at 100,000 K. So let's do that. Let's erase this. Okay, and we have the rate constant as 0.072. Sorry for this writing, because I'm using mouse to write, but I hope you understand that 0.072. This would be equal to the A using RNAs, e to the power minus EA. EA we will put it, just wait a second, by RT. So if this term, if you see, we can put this term over here on the left hand side and calculate A. So my A would be equal to 0.072 multiplied by e to the power EA is 82 kilocal per gram mole, so 82,000 cal. Okay, just remember the units are in cal, and for cal the R value is 1.98, I think. I just remember it to be 1.98. Let me check. Ideal gas constant, yeah, in kilocal, yeah, it's 1.98. In just if we use cal, then it's 1.987. So 1.98 is good, and into 1000, so it's given at 1000 Kelvin, it's given. Okay, so 1000. So this 1000 and this cancel out. Let's calculate this part. Yep, So 82 divided by 1.98, that's 41.4141. so let's take e to the power 41.4141. yeah, okay, it's quite large, but let's just multiply it with 0.072 and we get this value. Yeah, it's quite large, but that's the thing. Let's just copy this, go over here, put this value, and for E we have in cal per mole, so cal it's 82,000. yeah, 82,000, it's okay. So let's just proceed. Reverse order, it's 00, there is no reverse order. Rate is in the seconds, that's important, so kilomole per meter cube, because kilomole per second we have, so that's also correct. Volume would be in meter cube, no need to worry. Just click on OK and let's go to DWSIM. So we have this in my reaction set. Let's add the reaction of this thing and let's click on OK. So we added the reaction in the reaction set. Okay, so we will choose this one. Let me just run it so that it refreshes. Okay, come on, please refresh. Sometime it takes some time to refresh this one. The R1 has this. Okay, it's active. Yes, let me select something else, then go to this. Why isn't it coming? Anyways, let me see the product, this. Let me again make the PFR. Let's delete this. I think it's kind of a bug. Let's delete it and put it again. Okay, PFR, and we have, yes, now we have R1 and it would be isothermic. Now we need to mention the dimensions. So here this is the important thing, that we need to guess a particular volume. Okay, and according to this volume we will get a particular conversion over here when we run it. Sometimes, let me just show you, let's not tell you. So let's say my volume would be 1, or let's say I keep it as it is, and let's say we run. So you can see here there is an error, and the error is this thing, that the OD solver has failed. Now if I like make it like 2, okay, like 23, so again it will say, sometimes it might say that the pressure drop is too high, okay, or something. Okay, let me just go to this thing and specify this, an isothermic, and I think the feed is okay, 11505 atm. Yes, so here the most difficult task is this dimensions. Let me take about 2, and that why you need to just reduce the tube length and try. Okay, it's not working. Let me go to this thing and check my reaction is correct. So all are selected, and this is done, this is done. Okay, it should be my vapor phase. Yes, because at this particular temperature it will be all in vapor. So let me click OK, select, run. So these small things you need to check. Okay, now it's saying the pressure drop inside the PFR is too high. Now the pressure drop would be too high if my like tube length is too long, so the diameter would be very less. So let me take it kind of this. Yeah, it's done. So you need to just reduce the tube length. However, if you see that my conversion is 98%, okay, quite big. We just need 60%. Okay, so and you can also get the conversion concentration profile over here. but the important thing here is that the conversion is quite high, so we need 60%. Okay, so what we'll do is, now the most important thing comes into play, that is my sensitivity analysis. So we will go to force flow sheet analysis and go to sensitivity analysis, a new case 0. Take my object to be PFR, and the property would be, now we need two independent variables. Independent variables means I can change. Okay, it starts with I, independent starts with I, so remember I can change, so something that I can change. Okay, so what can I change? I can change the reactive volume and the tube length. Okay, so I can change my volume. Where is the volume? This thing. And I can also change my tube length. Okay, and then we need to take some lower limits. So don't take it 0 because volume cannot be 0, right? Let it be like 0.01, or let's say 0.1. This would be 0. Let's say 5. No, the volume is like 2 now, so let's take it 1, 2, let's say 2. Let's take 5 points. Let's take lower limit, so it's like 0.1, so let's 0.05 to 0.1. Okay, 0.1 is the highest. Even we don't need this 0.1, we'll take, let's say 0.8, because 98% is too much, so even decrease this bit. Okay, you need to just tune these values according to your, like, kind of guess something, because this is 98%. So we need to decrease this, because when we decrease this, we were able to get a better pressure drop. So let's just try out, and this dependent variables is my conversion. So PFR, and PFR, I need my ethane conversion. Okay, go to results and start. Okay, so here we see it's quite high. So let me break it, and if we see the PFR volume is 1, and at tube length, as we increase the tube length, you can see it's decreasing. Okay, so conversion is decreasing as we increase the tube length. So we should actually increase the tube length, but as we increase the PFR volume, the conversion is high. So 1 is quite high. We need to take it 0.1, and let's let it be 0.9. Let's try it again. Okay, I think there is an error. Okay, yeah, it's 25% too less. We need to increase it, let's say 0.4. Let's try it again. Okay, 0.4 is like very close. So 0.3, 0.3, and hopefully we will get it now. Yeah, just there. So it's about 0.3, then 0.45. So let's take 0.3 to 0.4. Okay, and let's start it. Yes, this part. So it's about 60% over here, and yes, this is quite near. So 0.35, at about 0.35 meter cube of volume with a tube length of 0.065 meter would actually give us the ethane conversion of 60%. If you want to take even more, so we can take 0.34 to 36 and take different tube diameters. So 0.34 to, let's say, 0.36. We can even take like 10 points and find out more actual value, a very close value over here. So overall, like, we get it's kind of like 0.34. okay, yes, that's kind of a very close value, 0.34, and we can take the 0.34 as the answer. So this is how you like get this. Now you can just put this part over here, the 0.34, and we can also put my tube length to be 0.02, and let's just go to my flow sheet and solve the flow sheet. You can see this particular conversion percent. You can also like save this image or show in another window. This is how the profile would be, and we can see the ethane is decreasing, ethylene is increasing, nitrogen is going somewhere, I don't know. Anyways, the important thing over here is that this is how we get the reactive volume. So I think it's clear. In the next part we will see how to do the hand calculation. So thank you, and make sure you like, share and subscribe. Please subscribe and show some support. Thank you.